So thank you very much for the opportunity to give a talk in your uncertainty quantification seminar. And yeah, Alex told me that he has read a lot about a lot of papers from my PhD supervisor, Erich Nowak. So while still there might be people around that have not dealt too much with the detailed theory or might require a recap. So let me introduce you to the kind of setup I want to talk about. So I want to talk about numerical integration. So the task is now I have given a function f from some function class of integrable functions in d dimensions, so in d variables defined on the unit cube. And I want to approximate the integral of that function using n function values. So there might be n function evaluations at nodes x1 to xn. They may be random, so I capitalize them. These are random variables. And then there is some method. It is also maybe random, some mapping phi that is going to use these function values and yield an approximation of the integral. Could be a linear mapping, could be something non-linear. And of course, the way it's using these function values also depends on the randomness on the positions of those function values. And yeah, so having such a method and when it's randomized, how do I assess the quality of that method? I need to define a notion of an error. And the standard notion of a Monte Carlo error is something like the root mean squared error. So it's the squared distance between the actual value of interest and what the algorithm yields, the expected squared distance, and then the root of it. So it's called the root mean squared error. And now I consider the error over a function class. So I take the supremum over all functions that are bounded by one with respect to the norm of that function space W. Now, in this talk, I want to take a different approach, namely it's the probabilistic Monte Carlo error at given uncertainty level delta, and works a little bit differently. So the probabilistic error of an algorithm AN at that confidence level 1 minus delta, or the uncertainty delta, this is defined as the smallest epsilon, such that I can state that for all functions from the unit ball of that function space, we have a probabilistic guarantee of the type that epsilon is exceeded only with a very small probability, at most delta. So I take the infimum of all epsilon to really see, okay, what's the best possible guarantee that I can state on this algorithm. And yeah, so algorithms, there are many options, but of course, I'm not only interested in the error for a single algorithm, but also the optimal algorithm that uses n function values. So I have the same error notions here, and I just indicate with MC that all Monte Carlo methods are admissible in this situation. And here I take the infimum over all admissible algorithms and these definitions of the error. The same happens here for the probabilistic Monte Carlo error. So it's the question, do we find an algorithm that can give such a probabilistic guarantee? There are also modifications that some people only consider the expected error, the mean error. But in a sense, that is not much different from the root mean squared error. So much more analytical difficulties arise with the probabilistic error criterion down here. So the distinction between root mean square error or expected error, no matter how you want to take it, this is not that crucial. The crucial part happens here when we switch to a probabilistic error criterion. What kind of function classes are we considering? So we want to have a complexity setup. We want to say something about a class of functions. So a typical one is Sobolev spaces, isotropic Sobolev spaces. These are functions where LP norms of certain partial derivatives are bounded. And we take partial derivatives up to a total degree of S, and this is S is the smoothness. Yeah, and these weak partial derivatives shall be LP integrable, then P is the integrability. There is, of course, also a usual modification for infinity. So there is the essential supremum we take here, or the maximum of all these partial derivatives. This would be the infinity norm, but these are the usual modifications. But the interesting part is happening for P smaller than infinity. And before I want to talk about what we've shown, I want to make you familiar with typical results we would get in this kind of theory. So first I restrict to integrability greater or equal than 2, because there is a clear speed up of Monte Carlo. So there is another assumption to simplify the results, namely that I have higher smoothness, which is enough that I know that I can find continuous representatives of the functions in those Sobolev spaces. So they are continuous. And then when they are continuous functions, then we can give deterministic integration rates. It looks like this, n to the minus s over d. So smoothness s is there, and we have it divided by the dimension d. So higher dimensions are more difficult. We need more smoothness to compensate for the high dimension. It's only about the rate, so there are probably some constants involved. So there might be an estimate with a constant C1 times n to the minus s over d is smaller or equal than this error quantity, smaller or equal than another constant times this expression. This is what this statement with the weak asymptotic equivalence is meaning. There is here, with the integrability being greater or equal than 2, there is a usual speed up in the rate by 1/2 once we use Monte Carlo methods in the standard Monte Carlo error notion with root mean squared error. So this is the usual speed up. But if we consider the probabilistic Monte Carlo error rates, we do not only have a dependence on n, the number of function values, but also on the uncertainty level delta. And so there is a speed up. You see here, it looks like this. So we have not only a speed up of n to the minus 1/2, but it's a fraction of logarithm of 1 over delta divided by n, and then the square root. So this is a more precise way of stating what Monte Carlo can do. And as you might notice, if delta is too small, then this might be an expression greater than 1. And if this is the case, this would be worse than the deterministic integration rate. Of course, this should not happen. So we want to have, if delta is too small, then we are basically in the worst case setting, and we can fall back to the deterministic integration rates. The probabilistic result is in a joint paper with Daniel Rudolph from 2019. I just want to state, okay, also we do have results for smaller integrability, and well, as long as p is greater than 1, there is a speed up. If p equals 1, there is no speed up, and it looks very similar, the result. It's just another power that we have. It's a little bit less of a speed up with lower integrability. So this is how results look like. Let's focus just on this. Remember this, the fraction logarithm delta to the minus 1 over n, the square root of this. This is the kind of speed up for moderate uncertainties that we are expecting. And of course, these constants here, they are independent of delta and n, the constants involved in this asymptotic relationship. So it's a joint asymptotic, joint of n and delta. When we started studying this, we realized, well, many methods, the way we have constructed them, they have comparably fat tails, or if we only know about the variance of them, we can maybe use Markov's inequality to get some probabilistic error bounds, but they are not really optimal. They would be polynomial in delta, but the typical rates you would expect they are logarithmic in delta. But there is a way, if you have some method with heavy tails, that you could still produce a method that has better probabilistic guarantees. Namely, maybe using Markov's inequality, you can find some epsilon, for some epsilon that the probability of exceeding this epsilon is bounded by 1/8. So this is some kind of initial delta. And this delta will be pushed down by repeating that method k times and taking the median of all realizations. You might think in statistics, many people should be familiar with such kind of median trick. And well, the effect is the more repetitions I take, the smaller the probability of failure gets. It's decaying exponentially in k, the number of repetitions. So which is actually something quite useful. But be aware, this is a nonlinear feature, what we have here with the median. So this is probably not the nicest method. It introduces a bias, but still, like, if you don't have anything else, it's still okay to do this. And we have a corollary where we were just using that we had several results on the expected Monte Carlo error. There was also for discontinuous functions, there were results by Stefan Heinrich that extended previously known results, where it was just for functions that are embedded in the space of continuous functions. But it's very general. We have a rate here, and then applying the median trick, we can get something like this. This is an upper bound. We have this ratio of logarithm of delta to the -1/n, and this raised to some power. Now, the convergence rate in n is optimal, but the problem here is that this logarithm of delta to the -1 is also risen to the power s/d plus the speed up, and we would only want it to be raised by the speed up, not by this smoothness dependent term. So this is a little bit too much. This additional component in the exponent is too much for the logarithm of delta to the -1. So this is probably not optimal unless we have smoothness 0. And this is the case for the backspaces. So there we can get optimal rates for approximating Lebesgue integrable functions from LP spaces. Yeah, this is okay. How do we achieve this? This is just the median of means. It's I think it gained some popularity in recent years again, but it's known for a longer time. I think we have the median of k repetitions of a standard Monte Carlo method that uses m function values each. So it's just the average of m IID function values. This is a standard Monte Carlo method, and I take k repetitions and take the median of those. This is the median of means, and here I can achieve that rate. So yeah, there's a question.
Quick question. Yeah. So m times k is n in this case, or how does it work?
So m times k is the number of function values I use in total.
Okay.
Yeah. So and the way is, like, how do I need to adjust k? Basically, k will be something like the logarithm of delta to the -1. It's proportional to this quantity. K is proportional to this quantity, and then it works.
Thank you.
So we were using this method in some other famous approach, it's control variates, and we combined it with a median of means. So there we had for sufficient smoothness, so that we have continuous functions. I showed you that for different integrability parameters, we have different rates. I just subsumed this with defining p prime, so that I can write this speed up in just one expression. But it's exactly what you've seen before. We can achieve that. So this is the result you've seen before. And the question is, how did we achieve this? So we had given a budget of n function evaluations. And the idea is to spend half of the budget on a deterministic approximation of the function we want to integrate. So we evaluate the function in some nodes, have piecewise polynomial approximations, or whatever method for approximating we use. The main point is that the LP prime approximation is of a certain rate. This can be achieved. And then the other half of the budget is used to estimate the integral of the residual, so the difference between f and g. So for g, we have a representation in our computer. We don't need to ask for more function evaluations, but when we want to estimate values of this difference, we also need to evaluate the function f in some nodes, and this might require some costly simulations, depending on how function values of f are obtained. And well, yeah.
Just to understand again, this function g, you got it by a regression essentially, or some interpolation, that's what you mean?
Yeah, it could be some piecewise interpolation, something like that. They're very simple methods. We don't need it to be smooth. It can be polynomials on subcubes of the domain.
Good. So like there is no issue with the integral of that. You can just find it.
Yeah, so when it's piecewise polynomial, of course, you know the integral of g.
Well, it depends on the measure, right? If you assume that the measure is uniform, yes. But
yeah, we have the uniform measure, so it should be very, very simple. The integral was defined just as with a uniform measure. So
good.
In this case study.
Then it follow. Thank you.
But even if not, like theoretically, we have full knowledge about the function g. So we assume that we can compute the integral because we have a full representation of it, and it's not about evaluating the original function of interest. This might evaluating f might involve some PDE solver or stuff that it's very costly. But g, we have a simple representation, and we can deal with it in a very simple way. So the assumption here is we deal with it exactly, and it's in fact the case if we have piecewise polynomial interpolation and the standard Lebesgue measure for the integration.
Exactly, but there are many problems where the measure will be sort of non-tractable, right? I mean, that you will not get an exact thing. But again, in this context, it's perfect. Now I understand. It was just a clarification.
Yeah, I mean, we don't focus on how much algebraic costs we have evaluating this. We focus on the oracle cost for evaluating f. So this is the point of information-based complexity.
Yes, and also what is important information-based complexity is that you're using these balls, right? I mean, these balls in this functions, right? Because
of course, when we have function f with a higher norm, then the error bounds would scale accordingly.
Yes.
Because
now, what I mean that
are homogeneous or sometimes even linear.
Yeah.
This is non-linear. This is still like homogeneous. So if f is multiplied with a factor 100, then all the error bounds would be times 100 and all the outputs. So yeah. Here also I've written it down. K, the parameter of how many repetitions I need to use of the standard Monte Carlo methods on this residual. This is proportional to a logarithm of delta minus 1. And K times M is the cost. It should be approximately n half. It's just if we want to have a way too high confidence, we are basically falling back to the deterministic rates. So we are instead using deterministic methods. I want to point out that here the method does not only depend on the number of function values, but we also need to adjust a parameter depending on the uncertainty delta we choose, which is a little bit inconvenient because we want to have a good method, but we do not really know like what is a reasonable confidence level we want to have. We want to have it optimal for all confidence levels. It would be nice, but here we need to adjust it for a specific confidence level. And we've found out in that old paper that for certain classes, so for example, if we have Hölder classes, Hölder continuous functions, or we have Sobolev classes with smoothness 1, then a very simple approach of stratified sampling can already give optimal rates. So the idea is just I split the domain and I take one random function value out of each subcube. This is a very simple approach. I show you some sampled sets. It's a linear method because I just average these function values. It's unbiased and it's universal for all data because the way we prove it, the bounds is using Hoeffding's inequality. Due to the continuity of those functions, we have some absolute range within each of the subcubes. And so the function value here is a random variable, but it's bounded. And we can use this boundedness, apply this with Hoeffding's inequality. We only had results for integrability p greater than or equal than 2, but in a recent paper, I could show that we achieve optimality even for smaller integrability. There needed another version of Hoeffding's inequality. The question is, are there linear methods in other situations?
So just when you use Hoeffding, then what you're using is the uniform bound over the whole class of functions, right? To be able to use some kind of Hoeffding that is uniform with respect to all the functions in the class. Is that so?
Yeah, of course. Yeah, it's then a uniform bound for all functions in the class. But for individual functions, some might have more fluctuations in this subdomain. Some others might have more fluctuations here. But this is all accounted for. Like in total, just belonging to the smoothness class will give some absolute constants for the estimate.
Thank you.
Now what about higher smoothness classes? This was a big question. And yeah, the idea I was studying in a new paper I wrote last year in summer. This is about stratified contravariates. So the idea of contravariates was to approximate the function and then estimate the difference between the approximation and the original function with the Monte Carlo method. So we split it into subcubes, but here now on each subcube I have a polynomial interpolation of f. So I have these triangular shaped point sets in green. This is a very convenient way of setting things up so that interpolation is quite easy, straightforward, easily implementable. I have a polynomial on each of the subcubes. And now the idea is I take roughly as many random nodes from each subcube. So it's not that I have I spread the random nodes over the whole domain, which was in previously studied methods the way to go. But here it's the very simple idea to say, okay, now if I have n0 nodes to compute the approximation, I also take n0 random blue dots on each of the subdomains, so that on each of the subdomains I have the same amount of function values. And this helps to bound the random variables in a way that I can apply Hoeffding once more. So you have random nodes on each subcube and you average them for each of the subcube. You have each of the subcube, I is the index for the subcube, and then you have some IID nodes on the subcube, you average them. So in a way you could say you have a basic method using 2 and 0 function values, 2 times n0 on a cube, and this is scaled to a subcube, and I just combine this basic method for all the subcubes. So this is the way I also implement it. It's just repeating one basic method with fixed amount of function values, repeating it on subcubes and averaging the subcubes.
I'm sorry, I have a question.
Yeah.
Did you consider to take subcubes of different size and different number of samples in each subcube?
It's in this very basic setup, it's all the same. But of course, if you have more complicated domains, this idea, I mean, I want to make a showcase that this idea of stratified contravariates, like taking basic small methods on small subdomains and repeating it on other subdomains independently, this is a good approach. And I just want to show it with this very basic setup. But in principle, the idea, of course, should work for other domains. I mean, if you have an application, we can talk about that and let's see how it works.
And can you imagine to take it in hierarchical way? So you divide first in two, look, if necessary, you keep one large and subdivide second further.
I don't see the necessity for such a complicated approach at this stage because I obtain optimality here with a very simple non-adaptive approach.
Okay.
Yeah. It's a linear method. It's non-adaptive, I say, so I don't need to know which precise function I have. I only need to know which kind of smoothness do I want to exploit. Yeah, I need to decide for how big the degree should be of the polynomial interpolation on the subcubes.
I'm sorry. Your hope is that in small subcube you will have better function. Yes, smoothness will be higher. Yes,
no. The point is, it's basically the same approximation as before in the classical contravariates. It's just that for the random nodes, I do some kind of stratified sampling. So it's because maybe there might be some subdomain where the approximation is worse. My contravariate, so the polynomial based on the green nodes is worse in approximating f in some of the subcubes, but I don't take by random sometimes more or sometimes less function values from that subdomain, but always the same amount. And this helps to reduce the fluctuations in my random part of the algorithm.
what it's a little bit unclear. I think it depends on where this function has, for example, singularity. Because near singularity, one expects to take more points far away from.
It's in this perspective where we have the worst case over a function class. Then the singularity, not singularities, but the difficult parts could be anywhere. Like I don't know. I don't have more a priori knowledge. I just have the knowledge the function belongs to a smoothness class, and this is what I work with. If I have other a priori knowledge, of course, I would think about other methods. But here I'm considering the supremum over all functions from a certain smoothness class. So
thank you. Clear.
It's not that I have adaptation to a certain part of the domain where something weird could happen. And actually in this setup, I assume that functions are smooth, so I don't have actual singularities there. So here, some more pictures with other random nodes. You see the green dots stay put, but I have some random nodes that move to random places, but there are always the same amount of blue dots in each subcube. And with this, I could show, okay, there is a family of linear algorithms. You've seen the nodes on the previous slide, and they achieve optimal probabilistic error rates. So the family does not depend on delta, so it's just depending on the number of function values I have, the budget, and I achieve the optimal rates I was aiming for. And the point is that for local approximations, I'm interested in how big is this residual? How much can it deviate? Is it so the random samples there and the random function values are these bounded random variables? And these can be bounded with a local Sobolev norm or local Sobolev semi-norm. And this can be put together. So on the whole domain, I can compute the Sobolev norm. So I can bound these absolute bounds of the random samples for the residual estimator. I can bound these in terms of the Sobolev norm. So in Hoeffding's inequality, I need the squared sum of these. I can use Hoeffding's inequality to bound this, then I can apply Hoeffding's inequality. So this is basically how we exploit this. I don't know whether on a single domain, this norm might be bigger on a certain subcube GI, but I know that when I put everything together, I can bound all these together by the function norm of the by the Sobolev norm of the whole function on the whole domain. This is like the crucial point. I was saying I was using Hoeffding's inequality, but there was a difficulty with lower integrability. So normally you have, if you have function random variables that are bounded each, so each random variable is bounded by some bound bi, you can write a vector of these bounds, and you are interested in the average expectation of these random variables. This is where Hoeffding's inequality can tell you something about the probability of having an error greater than some epsilon. And it's this exponential type of bound where you have the L2 norm of that vector of bounds here. This is what we have there in Hoeffding's inequality. And there is a version of Hoeffding's inequality that I included in my paper. I'm not aware if someone else has proven anything comparable for this, but I want to show it to you because maybe you have never stepped across a problem where you needed it. But here, because I'm talking about Sobolev classes of different integrability, like also integrability p's between 1 and 2, there I needed something different. And I have something similar, some similar bound, but here I take the LP norm. It's for p between between 1 and 2. P between 1 and 2, I can take the sequence norm here, LP norm of
That's
the
very cool.
vector of bounds. Yeah?
Yeah. I find it very cool.
Yeah, it's something you probably may have never used. The crucial idea is when I have a vector bounded in like an L 1.5 norm, there might be few entries that are really big. And the trick is just to say, okay, for these really big entries, I just assume that they produce the worst case error. Like there is the big deviation happening for those random variables with where the bound bi is very big. And for the remainder, these are again small values. And then I can use Hoeffding's inequality for the small ones. So I combine some worst case pessimistic estimate for the very widely spread random variables. And I use Hoeffding's inequality for those that are more contained. And I can show such a result. I also translated it in a more easy to read way if you're concerned with complexity bounds. So you write delta on the right-hand side. So the probability of exceeding this expression here is bounded by delta. And here you have something where you have the L2 norm of B, and here you have something where you have the LP norm of that vector of bounds, and appropriate expressions in delta. You see, this is the speed up exponent we were aiming for. And here you have the square root. So it actually looks really nice and comparable. We lose something here, a factor of 3, but it's still something we didn't have before.
And still you're getting a rate 1 over n, essentially, in terms of the number of evaluations.
Of course, this vector here, when analyzing the function integration problem, this also includes something on the amount of budget, because the budget n also tells me how many subcubes I can form. So when I have more subcubes, of course, the bounds are smaller for each of the subcubes. So there is something of n also involved here, but this is the lemma in an abstract fashion with random variables. Of course, you have different random variables once you have more subcubes.
Yes, but I mean, you could think still that the vector be summable, essentially that the LP norm of B is just a constant, is bounded, because
No,
I mean
it's not a constant. It depends on when you apply this, you have situations where this also depends on n.
Yes. But I mean, you may have information, a priori information, and you change then the set where this B actually could be of infinite length, but still the LP norm of this B is bounded.
Yeah, if you want to apply it in other situations that are not fed by some function integration problem, of course, you could still apply something like this. This would be interesting. Like sometimes you have this, sometimes you have that. So
yeah, no, I mean, because I mean, this LP is more natural because you were mentioning today the case of random PDEs, for example, right? But then these PDEs may come from coefficients, and the coefficients may come from an expansion, and the expansion has infinite length. But the B's naturally have some anisotropy on it.
yeah.
Means
So
that the B's, you can order the B's in such a way that the index I makes them to become smaller and smaller and smaller, and you have some information on which is the LP norm that is bounded for this infinite length B. And then you could use, I think, in this context, some information like that. But
yeah,
okay,
this would be really cool. Like
I
want
will
to
discuss it
include
later.
this lemma because I really thought maybe this is of use for some other situation.
Absolutely. That's why you got me my attention, because I saw the LP norm.
That's great. So maybe we continue this discussion later on. I would be really
Absolutely. Yeah, again.
Okay, yeah. So I just want to quickly mention also for functions that are not representable by continuous representatives, like if I have not enough smoothness, so we call it low smoothness, there is a way with some randomized interpolation. So I have a random shift in the interpolation nodes. You can still achieve something, but with this modified version of stratified contravariates, which is a linear method, you would have a polynomial dependence on data, because you have functions that are discontinuous. They may have singularities. So probably non-linearity in terms of using the median trick or something like that would be necessary to achieve really good confidence. But I studied linear methods in my recent paper because, like, once you study linear methods, you want to see what is the power of linear methods in different situations. So it also works for a case of less smoothness. I think I don't need to go into the details. I want to give you, in the remaining minutes, I want to give you a little bit more insight in how do I prove optimality, how does this work in that branch of information-based complexity where Erich Nowak is also working a lot. So I wanted to show a lower bound that is actually what I've shown as an upper bound. It should look the same. It's a different constant here. So this means it's greater or equal than a constant times this expression. And so I consider a set of functions, it's a finite set inside that Sobolev space, and all functions in that set are bounded by 1. So it's part of the unit ball. And I take the uniform distribution on these functions, and then the point is, for any algorithm, we have here, this is the failing probability for a randomized algorithm, but we take here the worst case over all functions from the Sobolev class. And this can be lower bounded by the infimum of all realizations of that method. But here I take the mu probability of picking a function from that discrete set such that the error epsilon is exceeded. So this is a failing probability with respect to an average input setting. It's a trick also known as minimax principles by Yao. Yao's lemma, also known as Bakhvalov's trick in the IBC community. So Bakhvalov was a Russian mathematician who studied Monte Carlo integration in the mid of the 20th century already. So it was already used very long time ago. And here it's now about failing probability instead of considering all kinds of difficult randomized algorithms, I can just consider deterministic algorithms. But this is really what's happening. If I have a method and I take the infimum of all random seeds, it's basically considering a deterministic method. The best deterministic method, I can replace the infimum by the infimum over all deterministic algorithms instead of just one fixed realization of a randomized algorithm. And this is much easier to study what is possible in such a situation. And I want to spare you the details of analyzing such a setting. It's possible. It's a little bit technical. The main idea is what kind of discrete set do we look at? And here we have few bumps for low integrability. So you take some of the subdomains of a function class. Yeah, you have a function class defined on an interval in this drawing here, and you put some bumps on some of the subintervals, or imagine subcubes. You have a bump function there, and with random directions. So it could be several times sign up, several times sign down. Yeah, in a sense, you see in random locations. And if I have more higher integrability, then there is some transition happening for another. There are other rates happening. You see there is no additional speed up for higher integrability. So there's a limit for Monte Carlo what they can do. And it's essentially here then we take bumps everywhere just with random signs. And it's the task of an algorithm like to know the integral of such a function. We need to know how often do we have sign a plus sign here and how often a minus sign. And of course, you can only learn about one of the bumps with one function evaluation. This is something easy to handle. This is where you get bounds. So just to give you an idea how lower bounds are proven here. And this was for the optimal bounds, but for low smoothness, where I only had polynomial dependence on delta, there was a question, like I showed this, and there's a question, okay, if I have linear methods, is it always like this, that I don't have any way of bringing this to a logarithmic dependence on delta? This is what I wanted to show. So there's a question, are they matching lower bounds? Well, of course, if we fix delta, then the rate in n is optimal. This is nothing new. But the question is, okay, what is the delta dependence? And I could state something like this. If we fix a linear method, then with n function evaluations, if I fix a linear method, then there is some constant. It depends on the size of the set of nodes where I evaluate the function, so the amount of function evaluations I have. But this constant depends on the methods Qn, so it's not universal. It depends on the method, and but then if I fix the method, then I have some polynomial dependence on delta. So it's really in the slow smoothness regime, linearity does not give optimality. If I don't adjust in any way to the kind of confidence I want to achieve, then I have this problem always. And I even analyzed my method, the stratified contravariates. What can I show there? There was even a gap in higher smoothness. I realized I do not really have, probably the upper bounds are not optimal in that scenario. I don't know how to improve it. Maybe I skipped this detail because this is getting more subtle. I just want to tell you I studied also lower bounds to see how well did I analyze stratified contravariates, and also the question, is there something this for low smoothness, is this something we can improve or not? I don't think we can improve it much more. So if you don't have really smooth functions, you probably need something like the median trick. But the main message for taking home is, if you have smoothness, if you have functions that are continuous, but just, I don't know, a little bit rough, but still continuous, then I strongly believe that linear methods can achieve what you need. And I mean, I have proven something. It's always a question, how big are the constants involved? So in a practical scenario, it might be different, but from a theoretical point of view, if you have smooth functions, linear methods can do it. There is some concentration phenomenon happening. So to stress this, I ran some numerical experiments to study the speed of convergence. I had a function exponential 15x1 minus 5x2. So you see it's a little bit lopsided. It's defined on the unit cube in 2 dimensions. It's a very basic example. And I just, the quantity of interest, the integral will be 1. So this is the criterion of how I adjusted this constant c. So this is the structure. It's exponential. You have a lopsidedness in the the 0.10 in the unit cube or unit square is it. There is where the function values are the highest, and then it's of course bringing some high outliers in evaluating this. So this is something where confidence might be beneficial. And I only run these experiments with exploiting smoothness 2. Of course, this is infinitely smooth, but you have to decide for some smoothness you want to exploit. And this means just piecewise linear interpolation. So you have 3 nodes on each subdomain, and then you make a 2-dimensional linear approximation. 3 nodes, just in a triangular arrangement. Well, it's always with 3 nodes. And there, like when you exploit smoothness 2, the best rate you can hope for in the deterministic setting is n to the minus 1. And this is this line here, you see. And what you can hope for in the randomized setting is n to the minus 3/2. So you have the speed up of 1/2. This is this line here. And well, I just run 1,000 times each of the algorithms, like starting with just the basic method on the whole cube. So 6 function evaluations, I think, for different methods. I took the classical contravariates, which is just an approximation and then random samples from the whole domain. I take the contravariates with median of means. It only starts when I have enough function values because I want to take it with 11 repetitions. It's something like for delta being something like 1% failing probability. This is where k equals 11 is somehow optimal for k repetitions where you take the median. And then stratified contravariates, the green one, is the new method. And now here, the next run, this is with, I think with 4 subcubes. And this is then with 16 subcubes. This is with 64 subcubes. So always I split in each dimension into 1/2, like I increase the amount of subcubes in each of the experiments. So here for each realization, I plotted the error by a pale dot, and you see somehow how this is concentrating. The more subcubes you get, then the more a difference makes it to do stratified contravariants instead of classical contravariates. So here, if I only have 1 subcube, no, it's the whole cube with the basic method. Classical contravariates and stratified contravariates, they are the same method, essentially. But here, a difference starts to kick in. So here you have 4 times 4, so 16 subcubes, and you see a difference. So here the upper line is the worst case in 1,000 trials, and you already see like the green line of the stratified contravariates within 1,000 attempts. It's significantly lower than for the other methods. So because of this heavy corner 1,0 of that function, where the function values are really high compared to the rest, this is where the classical contravariates method is spoiled. And also you see the contravariates with median of means. It doesn't look that good. It doesn't look that great. It doesn't help that much in this specific experiment. I picked up this situation here where you see the big difference kicks in. This is 4 times 4 subcubes or sub-squares of the domain, and just made a histogram for all these different methods. So remember, the integral is 1, and we have here a situation where the error is often much bigger than the target quantity of interest. It's just to demonstrate the difference of these methods, but I didn't want to scale it too much. I wanted to have 100,000 runs to just show there is a difference in the tails. But of course, this is not enough function values that you would really use it to approximate the integral. It's just for the numerical experiment. You see, yeah, you have some. It's a little bit of lopsided for the classical contravariates because also the function is a little bit lopsided. For the contravariates combined with median of means, you see that deciding for a number of repetitions of a basic Monte Carlo estimator and then taking the median, I pay something. I get a bias, and it's also only enforcing that the error is in a certain area. So it's concentrating around something where I want to have a guarantee, but it's not really that the error. It's a bias that we introduce here. But the very simple method of stratified contravariates, you see, this is a really nice bell curve-like shape. It's really nicely concentrated. It's much tighter, and it's unbiased. You clearly see the difference in the tails. Yeah. So 16 subcubes. Histograms with 100,000 realizations. This is what we get. There are some extensions of this. I mean, I will probably skip this. So there are methods that have a more regular structure, but there's not enough randomness probably in them. I have a very specific method where I need to decide on what degree of smoothness do I want to exploit, but there might be some other integration methods like this is Frollov's quadrature that have more regularity, but probably not enough randomness for achieving high confidence. You can show this that function evaluations on a point set that is too regular bear the danger that you just hit gaps of very regular functions with some bumps and then some gap. So I'm still looking for methods that are maybe more universal, exploiting smoothness as it appears to be, and still have good confidence properties. There's still some research, still some open research questions, and I think I skip all this stuff with random methods that use only a very finite amount of randomness, so finitely random bits. This is another area, another topic I'm working on. But I think it's this main message. I would stop here then now. It's almost an hour gone. That I have achieved something where we have more concentration of measure around error 0. Yeah. So thank you very much.
Thank you very much.